Well, I think it's time to get started, but I'll turn it over to Nick, who's going to lead the meeting.
Okay, let me share my screen. Can you see my screen? Oh, thank you very much. Thank you everyone for joining the seminar. Today, I'm going to present one of my project associated with CRESP. So the title is Modeling of Stress-Induced Port Pressure in the Widowstone beneath Composite Landfill. This project I was working on since 2019, and at that time I worked with Dr. Benson, and he's not on the call today, but I also would like to acknowledge him for giving me a lot of suggestions. A little bit about myself before any of this, the contents of the presentation. I'm currently an assistant professor at the UCF in the Department of Civil, Environmental, and Construction Engineering. And I prepared one slide to show what my work is and my academia journey. And so I was I got my PhD in 2015 from University of Wisconsin. My major is geological engineering, and also I'm a geoenvironmental engineer. At that time, I got a lot of studies on the landfill liners, work with Dr. Benson. And after that, I got a short period working Southwest Jordan University as a faculty member doing some geology surveys related work. And then after 2018, I went to University of Virginia as a postdoc and start my journey with the CRESP. And since then, I did a lot of work with CRESP, and especially related to low-level red waste measurement and modeling of the flow and contaminant transport in the saturated and unsaturated soil. And then after 2020, I got my position now at UCF as an assistant professor. So here is just see some pictures about my what I'm doing. So some of my students doing the modeling work, we do the lab, and also we had landfill surveying. So there's some land in Florida, we have landfill sinkhole problems. So we have the ground penetration radar to detect the sinkholes, and also we fly drones, very fun, to capture the emission and also for landfill monitoring. So that's most of my work. And also outside the lab, I'm doing soccer and play with the local team, and get a lot of friends. Just spend my Sunday with some Sunday leagues. So that's pretty much of my life. So about this project, I would like to especially talk about some background. This project, I started work on this project in 2019, and this is a project related to a landfill called Environmental Waste Management Facility. In short, is EMWMF, located in the Oak Ridge, near the local Oak Ridge National Lab. So the landfill is for disposal of the cleanup project of Oak Ridge's cleanup projects and the disposal of the low-level red waste and hazardous waste. So you can see from this bird view, this disposal facilities has 6 cells, and under the cells they have piezometers, which is used as the pneumatic piezometers to capture the groundwater levels. And there's also a subsurface drain. This red dashed line is to control the groundwater underneath the disposal facility. So here, just show a cross-sectional area, like a view. You can see this is the waste, and this is the liner, and below the liner there's a geological buffer. Set the separation between the liner and the groundwater, and the geological buffer is an engineered layer that is specially constructed on the residuum, which is a highly weathered material of the fractured shell. Fractured shell is a bedrock. And in the residuum, slightly below the geological buffer, they put these pressure gauges in there, and to capture the groundwater levels. So here just show a picture where if you have this piezometers, if the water level is above this piezometer, you're going to capture the positive values. This is based on the hydrology studies. You know that hydrostatic condition, you have this positive port pressures if the water level is higher than the point of concern. And also they have this underdrain. This underdrain is to control the groundwater levels underneath the landfill. So in the regulatory agreements for the EMWMF, it requires the base of the liner, which is the black dark color here, should no closer than 3 meters above the groundwater table. That means the groundwater table should never be above this red dash line. That means the groundwater level should never hit the bottom of the geological buffer. So here's some problem related to that initiate this study. This study, there's a historical record that we find out that after a period of time of construction, there's no rise in the port pressure readings, but after filling, there's an immediately increase in the port pressure. And the port pressure, the magnitude of increase is about like 20 to 30 kilopascal, which correlate to about 2 to 3 meters of water. That means the water that's give people some impression that the water level is higher than the location of the piezometer, probably 2 to 3 meters. That's a very huge change in the groundwater levels. So people worry about this because this might give some impression that it's the groundwater rise that hit the bottom of the geological buffer. However, there's some other things that is now showing the consistent observations. For example, one is the underdrain. Here is if you have groundwater level increase, the underdrain flow rate should also increase because of you have the higher gradient and the water the seepage velocity is getting higher, so you get higher water flow out of this underdrain. But over the period, so you can see after 2007, there's no increase in the underdrain readings, especially although there's the data missing, but you will see there's no increase in the water flow from the underdrain. So there's some so this kind of inconsistency bring this project on the board. And so we need to solve basically two questions. One is to evaluate whether this the groundwater is rise or not. That means we need to evaluate the groundwater level underneath the liner of EMWMF. The second one is based on our assumption, this is a highly probably like a local issue, not a groundwater rise issue. If this is like a more local issue, what bring up this port pressure at the bottom of the landfill liner, and what are the mechanisms? So firstly, we need to solve the first question to understand what is the groundwater levels beneath this landfill. So we have another two lines of evidence. First is we get some pictures from the site. The site engineers take samples from the outside the landfill. They cannot directly dig into the landfill for samples, but they can use SPT, which is standard penetration test, to get split barrel samples and take it out, just to go and see what the sample look like. So they dig into the residuum, which is a highly weathered layer that you can see the sample is highly fine in the material, but it's not wet. It's wet, it's not saturated. Saturated means you're gonna have the water that freely dripped out of this sample when you take it out. So you can see this one is definitely not saturated. But this one is only like also another indirect measurement. We decided to do a modeling just to see what is the groundwater levels underneath the landfill. So we use mod flow to evaluate the groundwater levels underneath the landfill. So multi-flow is widely used. I believe many of you have heard about this, especially when you do the hydrological studies. For the multi-flow, the thing we need to do is we can use this model to evaluate the groundwater levels underneath the landfill, but we need to compile a lot of information in there. Especially, we need to have the site digital elemental model, that's DEM. So that means the elevation of the area, because the landfill is sited in the valley, and we need the elevation information is there. And also we need other things, for example, some initial work I had to start the calculation and the permeability of different layers, because there's a lot of separate formations. They have different hydraulic connectivities in there, and also recharge conditions and isotropy conditions in there. So all this information were collected and need to be collected to set up this model. And also what we need to compare is we set up this model, the reading can need to be calibrated. So we also have the existing monitoring well on site, and we can use the monitoring well data to calibrate the model, and so that you can get a reading underneath the landfill. So for these monitoring wells, they are outside the landfill. They're not. There's no monitoring well below the landfill. So you can use the point is to use the readings outside the landfill to estimate the groundwater levels underneath the landfill. So for the site DEM and the hydrological conditions, we get some help from Dr. his group at Vanderbilt University. And there's a model that also they created for another study for CRESP. And we use this model, it's called Oak Ridge Regional Model. And we get a telescope model, which is telescope zoom into the landfill area, especially cut it like a square, just cut this cake out. And we put the landfill footprint here and some other site information on top, so that we can adjust the recharge a little bit, because you never get recharge from the landfill, because landfill basically cover the top of the landfill covered area. You shouldn't have infiltration in there. And also we use the information. We created the initial and boundary conditions for this telescope model. The landfill is sited in the valley, and we create the boundary. For example, you have the infiltration, and the water needs to flow from the highland area to lowland area. Lowland area, we set a drainage boundary, for example, the rivers, so the water can flow in this model. And we set up this initial boundary and boundary conditions. Then we need to calibrate with the existing wells near the landfill site. So here is just showing some kind of overview of the existing wells. You can see there's many wells they set up here. The purpose is they set up this well for monitoring the constituents in the groundwater for environmental management. And we can also get groundwater levels readings from there. So in general, you can see from 2004, let's start with the starting up point of this construction, and start fading is about 2007. And then till now, about this one only shows 2018. But you can see the groundwater levels in these wells has no significant change for most of them. And even though some of them have slightly increased, but the magnitude of change is less than like half meters. So that is not like 3 meters change in the groundwater levels. So you shouldn't have anything that's changed that dramatically below the landfill. So some impression for us is this port pressure increase is a reason of some local issue, not a groundwater issue. But when we look at the results of the groundwater things, the groundwater modeling, you can see the same thing. For example, on the left-hand side, if you can connect those measurements from these wells, use the ArcGIS, and they give you some readings, give you some trend. This is not the perfect tool because ArcGIS just assume this wells, their waterhead is linearly connected. That's not true for most of the wells because the hydrological conditions in the subsurface is quite complex. But it gives you a trend that's showing the groundwater is flowing from this highland area, which is I think there's the ridge, Pine Ridge there, and the flow to the Bear Creek, which is a creek that is to the bottom of this figure. And also, if I run the mod flow, you can see this is this contour, that number showing the waterhead in meters above the sea levels. And you can see this, the higher number means the higher waterhead. The water flow is definitely flow from this area, from this Pine Ridge to the Bear Creek. So they show the same trend. And also what's more important is these values here, they can give you some indication because I know what is the installation location of this piezometers. It's about 309 meters above the sea level. However, you can see this these values from the mod flow, they are all lower than 309. So that means this groundwater level should be lower than this piezometer readings. So from this few lines of evidence, we believe this is the issue is not related to the groundwater rise, but what is the cause of this port pressure increase in these piezometers? So this need to be dig into for more details because we want to understand the mechanism in there, be able to understand the problem. So I just forgot to mention this. This one just show another view. If you cut in the cross-sectional area, you can see this is a landfill, this is a geological buffer, and this is the groundwater levels. So there's still some distance between the groundwater levels and also geological buffers. Our approach to dig into the reason why there's some a change in the port pressure is we first brainstorm what's going to happen, what's going to increase the port pressure in the piezometers. So there might be several reasons. We think about several reasons. First is because the geological buffer is an engineered layer. When we construct the engineered layer, it should have some initial moisture content, especially as geotechnical engineer, we do a lot of compactions, and based on experience, we know that if they compact the soil into optimum conditions, the initial saturation should be around 70 to 90% of moisture. Initial saturation 70 to 90%. So that means a good amount of water that is in the geological buffer. And also this is in disequilibrium with the environment. So that means the moisture gonna migrate, either go up or go down based on the soil suctions in the geological buffer. So since it's compacted, you have finer porous media. So the pores are finer. So based on the water, like the surface tension, you created some capillary tubes. There might be some water go up into this geological buffer based on the initial condition of this engineered layer. So that might change the moisture content and port pressure readings in the gauge. The second one is the landfill is designed to supposed to hold some waste. So when you put this waste in there, especially if you put a lot of debris in there, the specific gravity of the debris are higher than soil, other like normal municipal solid waste, and it creates load on top. Higher load than other normal means the solid waste. And but the same thing is if you have this load on top, it's gonna load onto this soil. So this picture showing here is the soil grains and you have waters in there. So some water initially added for engineering purposes. This water well, so if you load it, the soil gonna have some deformation, and the area for this water, I mean the room for the water gonna be smaller, so the water gonna escape due to the load. However, if you see this soil is like fine material, you can imagine the permeability is low, and especially for geological buffer, the purposes is to engineer to a low permeability that so that if in case you have some contaminant that release, you can reduce the release to the environment. So that in general, that means you have a waste load on top, and the load is going to transfer to the soil and water, and the water cannot escape on time. So then the load is going to transfer the stress to the water. So the water going to have excess port pressure that might build up the readings in the port in the pressure gauge. So this is another issue, and we think this might be the biggest driver during that time, and also the seasonal groundwater periodicity, which is the groundwater is always fluctuating, and any soil that is above it needs to chasing the equilibrium conditions of this water fluctuation. So that also changes the port pressure. So that's a stream mechanism we dig into, and we use model numerical simulation building all these three mechanisms to evaluate whether the port pressure in the piezometer is going to increase due to the three mechanisms. So the simulation is we need to couple the stress deformation of the soil and also seepage conditions of the soil. So we use a finite element software called the GeoSlope that you can build in this constitutive model of the soil to build in the stress deformation conditions of the soil. And then you can also bring in the seepage conditions, for example, like hydraulic parameters, saturated hydraulic conductivity, and unsaturated soil hydraulic conductivities. So this is just showing a diagram showing what I did that time. We built up the model domains, the geological buffer, the residuum, and the fracture shell. Geological buffer 3 meters, residuum 0.5 meters, and I put these piezometers slightly below the geological buffer, and just to show just to watch what is port pressure increase at this point. So this one gonna compare with the PPO1 and PPO2, the piezometer readings once we run the models. And also the geological buffer and the residuum supposed to be in fine-grained soil and low permeability and a fracture shell due to its high fractured nature. So we put it high permeability. And we set up a groundwater table here. This groundwater table is obtained based on the outside monitoring wells. We put a 1.8 meter below the bottom of the geological buffer. Some parameters for the soil. So as I mentioned, you have the stress deformation behavior of soil. So here we use the Cambridge clay model. That's especially for the compacted clay. And we can use the site geological survey or investigation information, for example, consolidation data of the site material. We can use that to build up the Cambridge clay model. So that's really conveying the site real information. And then we have the hydraulic conductivity and a soil water characteristic curve by using by inputting those, we can have the hydraulic conditions for both saturated and unsaturated conditions. But mostly we're going to use is this hydraulic conductivity under different saturation conditions. So that will lead into how fast the water going to dissipate through the area. And also, also another thing important is we also bring in the stress dependent for the change in the hydraulic conductivity, because when the stress increases, the soil gonna consolidate or creep. Then the porous medium gonna be squeezed to a less void ratio, and then the water cannot flow very easily in the media, especially under the landfill scenarios. We have this waste fill in there is totally relevant to this phenomena. And we did some hydraulic conductivity tests before related to coal ash. We also observed for the compacted soil liners, if we have at different stress levels, for example, increasing the stress, then the hydraulic conductivity is going to decrease to maybe 1 order, 2 orders magnitude. So this one, we just bring in a function based on our previous study showing the stress increase. You also have a decrease in hydraulic conductivity in there. Some of these parameters are shown here: saturated hydraulic conductivity, low permeability for geologic buffer residuum, and a high permeability for the fractured shell. So after we build in these parameters, we create the boundary conditions. This model is set up in a simple way so that we can understand the mechanism easily. So as I mentioned, we created this model domain, and we input the parameters, and we also set up the boundary conditions. So there are 2 types of boundary conditions. One is the hydraulic boundary conditions, where is we set up the groundwater levels here. And for different simulation purposes, we can allow this groundwater to fluctuate over time, or we can fix it. So for example, if you want to see how the fluctuation affects the port pressure, we allow this fluctuate. If we don't want the groundwater to fluctuate, we just want to see the impact by stress, we just put it as a static condition. Another type of boundary condition is the stress boundary condition, which is on top. You can see on top we apply like evenly distributed stress levels. This is calculated based on the stress history, feeding history from the landfill. In the landfill, you know, they also recorded. They have tonnage data they recorded, so we can convert that based on the specific gravity of the waste and compute what's the stress history in the landfill. And then we especially just constrain this deformation into 1D because you don't want to let it collapse. So you just constrain to 1D, allow the settlement to happen if you have the stress conditions on top. So that's basically for that. And also on top, we have no flow hydraulic boundaries, which means you have liner, you never have the water flow back to the landfill. So even though you have built up, even though there will be high port pressure, it will not shoot into the landfill. So that's not a realistic case. So we set up no flow on the top. So we run actually a few simulations. So based on the 3 mechanisms we think that are relevant, those simulations are single effect modeling and a coupled effect modeling. So single effect modeling include the modeling, for example, like moisturing by the environment, see how this moisture migrate over different materials. And second model is to simulate the waste loading impact on the port pressure. And third one to simulate how the seasonal groundwater periodicity going to affect the port pressure in the piezometers. Then we couple them together to see whether this data, our simulation has good agreement with the readings from the site. So first one, we kind of studying moisture by the environment and see how this moisture migrate over time. So we have this one set up and constant water head below, and then we set up the geological buffer in there, give it some initial saturation. So this initial saturation is set up because we have a wide range of construction uncertainties. You have 0.3 to 0.9. That means 70 to 90% of degree of saturation. That gives you different metric suctions in the soil. So that means drier, you have a higher suction. That means you have a higher potential to pull water from the layer below or groundwater, and that means you can uptake water from the layer that's below the geological buffer, and there's no waste loading on top. So we do a simulation, several set of simulation. We can see if we observe the port pressure at this piezometer here, so the red circle here, the port pressure is actually increased over time. So for all of the cases, even 95% of the initial saturation. And for 70% of saturation, the water level, the port pressure increase is the strongest. That means initially it's drier, you have higher suction, you uptake water and takes more time. And especially we set up a 1-year timeline here. We cut it here because the landfill construction of liner, it probably leaves 1 year for the construction of the geological buffer till the fillings. You will not have like 10 years time just to leave everything not filled. So we think the 1 year would be a good timeline for this simulation. So we take an average value for here. So for different saturation degree, we take average, we see this average port pressure after 1 year will become to about 121.8. This is a minus value. That means the suction values here. So we use this value as a starting point for the coupled model to just simulate if we couple everything together, what is the stress condition, what is the port pressure going to look like in the piezometers. Also, the second model is the effect by the waste, the loading of the waste. So this one, we also set up a static water head here and apply the load. So here we assume the load is linear because it's not quite like realistic in the field, but it's a best estimation we have based on our the record from the tonnage data. So the linear, we assume it's linear. So this black line showing the waste loading, and we can see from time 0 is increase and then fill to 4.7 years. This is actually the period we observed the water pressure increase, and also we add additional 2 years in there. Just see how this is going to respond, how the port pressure going to respond to the waste load, and then we see a big change in the port pressure, and it start from negative, and then increase the load, and then port pressure increase, and after the filling, the port pressure is stop increasing and is decreasing over time. That means we build up some excess port pressure, and after we stop feeding the load, feeding the waste, the water can dissipate over time, and then port pressure also decreases. It might take a long time, 10 or 20 years, just to dissipate back to its original port pressure. And again, this geological buffer is not saturated, so it's unsaturated and then become a positive value, just very similar to what we observed in the field with piezometers. Also, if we put this piezometer at different depths, the impact going to be different because the closer to the load, and also the further to the more permeable area, the response is the response magnitude is higher. For example, if I put piezometers more closer to the liner, it's the response is the blue one, which is a higher magnitude of pore pressure change. If I put this one in the fracture shell, that's highly permeable area, then the water going to dissipate very easily. So that means if I put it further from this fracture shell, the flow path is going to be longer. So that also lead into a longer dissipation time, and the pore pressure response is higher. So this is for the waste loading. And then we also look at the seasonal groundwater periodicity, changing the groundwater with the site recorded groundwater periodicity. So groundwater fluctuated over seasons, and we also allow this pore pressure response to this seasonal changes. And we can see here is this is the input value from here. So the groundwater is kind of going up and down, but never hit the bottom of the geological buffer. We can see the orange one is showing the piezometers at the reading from the piezometers. So we can see there's a very negligible lag behind this groundwater periodicity. That means you can see the waves pretty match each other, and also the magnitude also match very well with the groundwater seasonal periodicity here. So show the input here, also if we have the piezometers installed at different locations, the responses are also different. For example, if we put it into a more permeable layer close to the groundwater table, and the responses is more like stronger responses to the pore pressure change. And if we put it further to the groundwater levels, more closer to the liner, again, no changes, no visible changes there. So, so this also gave us some hint if we install the piezometers, better to install it to a location where you have high permeable zone, and also not very close to this liner here. So the reading is gonna probably gonna misleading some of the indications here. So based on the understanding, we see the three factors, they all impact the groundwater, the pore pressure in the piezometers. I think especially the waste loading increase the pore pressure from negative to positive. So if we couple them together, what is the phenomenon, and how this phenomenon can match with the site readings? So this is the last task we do, is couple them together to see whether our model can match with the pore pressure measured by the piezometers. So here's some results we showed here. So actually I split them into the three individual impacts. For example, moisturing and also groundwater fluctuation, this black one. This black one coupled the groundwater and moisturing, and then we have a waste loading on top. Then what is the change in the pore pressure? So so the orange dots are showing the field measurements. So moisturing by the environment, it doesn't really bring up the groundwater levels. The pore pressure to the positive numbers, and also when you have the groundwater levels coupled, it also doesn't show the higher pore pressure than positive pore pressure in the piezometers. But when we add the waste, the loading inside in there, so you can see when we start this, it's the pore pressure increase very quickly, and almost at the same time it bounce up to positive and reach the peak there. And there's a short period at the first filling stage, as I mentioned, the first 4.7 years, then it decreases. And then we also had another data showing the second filling stage, which is around 2017. And there's another increase in the pore pressure. That means there's another additional fading. They have some soil that is piled on top of the cells. And we do see another increase in the pore pressure. And also we build that into the model as well, another increase in the waste loading. And we see another spike here. So that means the pore pressure correlated with the waste fading very well. That's kind of majorly the waste loading is the big driver for this pore pressure increases. And also after that, after about 2017, we do see this dissipation of the groundwater, the pore pressure. So this showing a continuously decrease in the pore pressure over time. So although it's not showing value that is close to zero, but it might take some time to get to the zero. But we do see this phenomena is this water excessive pore pressure is dissipating and getting to the original value and equilibrium with the surrounding environment. In general, we think we have a good agreement between the prediction and field measurement, and also the in some conclusion is the pore pressure that measured by the piezometers that are due to the excess pore pressure rather than a rise in the groundwater table. And we evaluated the three possible reasons, and also we coupled these possible reasons. And these reasons including the moisturing by the surrounding environment and the waste loading and seasonal groundwater periodicity. We find out they both affect the pore pressure, and especially the waste loading and increase the pore pressure dramatically to the positive values. And also after that, there is after the fading period, there might be a dissipation of the groundwater, the excessive pore pressure, and it might take up to about 30 years. That means a very long time. Also, plus the soil, the residuum, and also the geological buffer is under the high stress, and the permeability can be low, so it might take a long time to dissipate. So that's the major conclusion for these studies. So just final, I just want to acknowledge some of my collaborators, Dr. Benson, especially helped a lot on this research. His Oscar helped with the model, and Q, he's also here today and also start on the first phase of this study. So thank you very much for your patience to listen to this presentation. I hope this modeling part is not too confusing for all of you. So.
Thank you immensely, Nick. That was a great presentation. I guess I'll start off with the first question, if anyone has a field for it. So we talked a little bit about how the groundwater levels can affect the porosity of these. Is there been any consideration, kind of harking back to the conversation we were all having initially? Some areas are getting not enough rain, some areas are getting a lot of rain now. Is there any thought to work dealing with effects of climate change in these containment vessels?
Yeah, I think so. I think especially for this one is related to, I think, this in Oak Ridge. I think there's some way they do to control the groundwater is use this the subsurface drain to control the groundwater, and also I think we also did a study evaluate how this location of let me just go back, how this subsurface drain, its location gonna control the groundwater levels, because you will have some location have higher groundwater levels, like Florida, somewhere have deep groundwater levels. For the high groundwater levels, subsurface drain is very helpful. We do see that if you put it into a higher permeable zone and locate it into a reasonable distance, you can control the groundwater level to a fairly good levels that is probably like equal to this under drain levels here. So so you can have good control of the groundwaters. So that may be one of the kind of solution to different like climate. Yeah, thank you, Josh.
Yeah, of course. Thank you for answering. Anyone else have any questions they'd like to field?
Nick,
Yeah,
I have a question. Very nice presentation, not confusing to me at all because we are in the same field anyway. I have one question. So I know this project has been found many years ago. So do we still have more information about the piezometer? So how the piezometer work? Or all the research is based on the assumption that the piezometer is measure the pore water pressure. But when we apply load at the top, they will increase the pressure. We call it total pressure in soil mechanics. So is then possible that the piezometer measure the total pressure or part of the total pressure, not only focus on the water pressure? So if you have information about how the piezometer work, or whether we can calibrate the piezometer.
I think you're right. I think the piezometer may also have those total pressure, because in the site we are not sure. There's a lot of uncertainties in there, especially when we pack the piezometers in a soft fine grain materials and you put benzene on top. There's probably like you have water pressure, excess pore pressure, or you can have air pressure in there that also bring up this the readings of this piezometers. I don't know how to calibrate this, to be honest, for this one, especially for this project. But I think there's some discussion about this. This piezometer installation is probably not an appropriate installation. So that may give some other indication for future how to install the piezometer in a better location for other facilities. So.
Yeah, so if we can order the piezometer used in the field and put into unsaturated soil, and we can apply the load at the top, we can see what kind of response we can obtain from the piezometer. This can give us some information, so if you can affect by the total pressure or the water pressure.
Yeah, thank you. I think it's a good point.
Hi, Nick.
Hi, Chen.
Thank you for your great presentation. So this this study really helpful, for us to understand the reading of the water pressure at the field. So we have 3 key factors impacting the water pressure, right? Mm-hmm. Including the waste filling, the moisturing, and also the fluctuation of the climate conditions. Mm-hmm. I guess maybe the waste filling is the primary factor impacting the water pressure reading. So do you have the comparison between the modern results considering only the waste filling and the field data?
Yes, I didn't put it here, but I only do this. I just let's see this one. I have the filling data here.
Yes.
So I think it's about like 20 kilopascal. It's about quite close to the field measurement. I think mm-hmm. This one is the biggest driver for the pore pressure change here.
Yes, I guess this is the primary driver or the factor impacting the water pressure reading.
Yeah, and also I do see other people use the same type of piezometers in the dams. They also have this same issue. If they have the increase in the stress and the pore pressure increase a lot, but most of the time they don't consider this as excess pore pressure. They just take the readings. So I think our this study just based on our mechanism, we dig into the mechanism to see mm-hmm. The different phenomena. So that's a kind of results very interesting. So
yes,
thank you for your question.
It's surprising to see the good agreement between the modern results and the real data.
Yeah,
Thank you.
So Nick, this is Kevin. That's a great talk. So I know initially TDEC was a little suspicious of this. Did they finally come around once you were able to explain it to them?
Yeah, I think so. We finished the I think also this question for Craig maybe. I also
He's not on, so I'm asking you. I'm sorry.
Yeah, so we have more kind of explanations on the on this groundwater issue. So we use this model flow to also evaluate this. We put this model part in there. So that might be that's another line of evidence showing the groundwater level is below the piezometer of the landfill. So I guess this one also follow up with Craig on that. So, but
no, I understand. Like I said, I heard this secondhand from some TDEC people I knew. I told them they should look into it a little more because Craig was. You guys are the best in the world at this, so they may have been the actual issue, not this. So
yeah, there's like a no kind of you cannot really dig into the landfill to see what's really happened, but several lines of evidence showing the consistent consistent observation that
they had an issue with the underdrain. I mean, in Oak Ridge, typically you don't put things in valleys because they will bathtub. So I think they have the mindset is if you put anything in a valley, it's going to bathtub, and they didn't understand the actual what the piezometers readings actually meant. So this was, I thought, great work. Thank you.
Thank you, Kevin.
And as everyone probably knows, Oak Ridge is very wet. So even with climate change, you may get increase in frequencies, which may lead to some groundwater rise, but they get a lot of water at Oak Ridge. So they're used to dealing with water and issues related to water. So just putting that out there.
So yeah, so if so Josh, should we just wrap up or
Yeah, so if no one has any further questions, I think we'll call it there for today. Thank you all for coming out, and thank you again, Nick, for presenting. That was an excellent presentation.
Thank you very much for coming, and yeah, enjoy the weekend.
You as well.
Thanks,
Take care,
Josh.
everyone.
Thank you.
Thank you very much.